Good afternoon, everyone. My name is Pun. I will be the host for today's research colloquium. First, welcome everyone to join this section of research colloquium. Okay, so for today's sections, there will be 4 presenters presenting their research work, which includes Dr. Yeap, Dr. Lai, and Dr. Chai, and also Dr. Sum. So the first presenter that will be presenting will be Dr. Yeap Siu Ping. Dr. Yeap, are you here?
Yeah, I'm here.
Okay. So for Dr. Yeap, his topic will be evaluating the collider stability of graphene oxide nanosheet in heat transfer fluid. Dr. Yeap, you can start your presentation. Thank you.
All right, sure. Thank you, Jiajun. So, a very good afternoon to everyone here. So today I'm going to share with you about one of my projects working on the evaluating the colloidal stability of this graphene oxide nanoparticle in different type of heat transfer fluid. So later I will explain what is the objective and what is the problem statement in this research topic. But before that, as a beginning, I would like to acknowledge 2 of my students over here. Okay, Pang Yixiang was my final year project student, and also Kovi Xiang is actually currently my master student. So acknowledgement going to both of them, okay, as being a very back supervisor. All this while, I just like sitting in the office, then just give order to them by using the WhatsApp only. They are the one that doing all the dirty job, so they reserve my acknowledgement, okay. All right. Now, this will be my presentation outline. I will just begin with some introduction, problem statement, our idea and objective, the method that we use, and of course, the result discussion and also the conclusion. Graphene, okay, or graphene oxide nanoparticle is a 2-dimensional kind of nanoparticle that is made up of numerous carbon atoms that bonded together in hexagonal lattice structures. So you can see the carbon, they actually arrange themselves into the hexagonal structure, and it appears as a 2-dimensional structure. Okay, this will be the graphene oxide nanoparticle. Okay, now this graphene may present in the several derivatives. It can be in fluorographene, graphene, GO, radiographene oxide, graphite, or another one. Okay, so all these graphene nanoparticles and their derivatives actually are well known for their unique electrical, mechanical, and thermal property. Okay, they are well known for having this kind of property. That's why for the engineer, for the scientists, they love using this graphene oxide or the graphene nanoparticle for various applications. Now today, for my sharing over here, for this project, we are actually using this graphene nanoparticle for thermal application, Now, then come to the chemical engineering. When we talk about the thermal, definitely we remember this thing called heat exchanger. All right, now I go into the detail of the heat exchanger. This is one of the very conventional kind of the shell tube heat exchanger. Now, it's very normal that normally we are going to pump in some coolant, for example, in order to cool down your product stream. Okay, again, you are going to pump in some coolant to reduce the temperature of the product stream. Now, in fact, currently, besides using the conventional coolant, people also trying to add in a little bit of this graphene nanoparticle into the coolant. Okay, into the coolant. And in this regard, this structure is what we call as the nanofluid, whereby you already got your nanoparticle together with the coolant itself, the normal fluid itself. Okay. Now, in fact, it was reported that by just adding in a small quantity of this nanographene into the conventional fluid, it can actually improve the heat transfer capability. Now, of course, when it comes to chemical engineering, we want to make sure our heat transfer can be very, very high efficiency. Okay, and in fact, by just adding in a little bit of graphene nanoparticle, you can improve the heat transfer capability. Now, this research is not new. In fact, there is already some research found that by just adding in a little bit, okay, a small quantity of this graphene oxide into the water, for example, it can enhance the thermal conductivity by about 47%. So very successful. In another research, they found that by adding in a little bit of graphene oxide into this ethylene glycol water, okay, ethylene glycol and water is one of the coolant as well, heat transfer fluid, okay, and they found that the automobile radiator, the performance actually improved already by just adding in the graphene oxide into it. Based on all these iteration study, it seems like by using the nano fluid, it's much more better than using the conventional fluid alone, okay, by just using the fluid alone. So that's the reason now people try to add in this nanoparticle into the water, ethylene glycol, and engine oil, okay, instead of just using the water, ethylene glycol, or the engine oil alone, okay. Alright, so this will be the photo. For example, this one is a water that normally we use as coolant, but after the water is adding in with the nanoparticle, it turns into a black color or dark chocolate color, okay, due to the graphene oxide itself. So moving on, it seems like this research is very successful over the past few years. However, one of the things that the researchers seldom go to discover will be the agglomeration issue. Okay, agglomeration issue. Now, similar to other type of nanoparticle, the effectiveness of this graphene nanofluid for heat transfer application is actually depend on whether it can be stable stand inside the base fluid or not. Again, it's whether it's going to be stable inside the base fluid or not. Now, what does this mean? For all the nanoparticles, it's always happen that after you keep them for some time, you will see that the nanoparticles start to agglomerate. By keeping the solution for a little bit longer time, you will find that the nanoparticle agglomerated into a very big cluster. Now, this is something that we don't want it to happen, because you imagine if the nanoparticle try to agglomerate themselves into big cluster, they become very heavy and they are going to start to settle down. Do you notice or not? The nanoparticle already settled down. They separated from the fluid itself. Now, if this happens, definitely we no longer can use it for the heat transfer application already. The sedimentation part, they might clog into the shell and tip part. This will be the thing that is currently unknown. So far, most of the studies that applying graphene oxide-based heat transfer fluid only focusing on their thermal conductivity. However, information regarding the stability of this graphene oxide in different types of base fluid are scarcely reported. So that's the reason I started asking my final year project students to working on this area already. The first objective of this project will be definitely to synthesize a graphene oxide nanosheet from the graphite plate. We actually using this modified Hammer method. It's one of the very well-known graphene oxide synthesis method. Okay, and the second one, of course, we need to evaluate whether this graphene oxide is compatible or not. Okay, whether it's able to dissolve or not into different type of commonly used heat transfer fluid over here. And the last one, we want to know by changing the concentration of the graphene oxide. Okay, we want to see whether the graphene oxide concentration can actually affect or not on the colloidal stability of this nanoparticle. So again, I synthesize the graphene oxide nanoparticle, I put into the heat transfer fluid, producing this nanofluid over here. And the heat transfer nanofluid that I investigated is still water, ethylene glycol, polyethylene glycol, ethanol, and engine oil. These 5 types, okay, I asked I discussed with my final year project student, and we decided to investigate on these 5 types of heat transfer fluid because they are the very common kind of fluid that being used in heat exchanger. These 5 types of heat transfer fluid, we actually noticed they actually have several similarity and dissimilarity. Now, in terms of the distilled water, it actually is a protic solvent. Why we call it as a protic solvent? Because they actually have the OH bond over here, able to form the hydrogen bond. The same go to the ethylene glycol, they got 2 OH group over here, so it's a protic solvent, able to form the hydrogen bond. Same go to the propylene glycol, having 2 OH group, able to form the hydrogen bond. Same go to the ethanol, it's a protic solvent because it's having 1 OH group over here. But for the engine oil, one of the very common heat transfer fluid is called the protic solvent because it doesn't have any OH group. It's not able to form any hydrogen bond. So we want to see whether this hydrogen bond synergy can actually affect or not on the graphene oxide stability. So this will be the research method. The first stage, we actually synthesize this graphene oxide by using the modified Hammer method. So you can see all the chemical things now. Okay, we produce the graphene oxide, and we go to purify the graphene oxide, and we also dry the graphene oxide into a paper form. Okay, and later on, we just tear a little bit of this graphene oxide paper, we put inside the heat transfer fluid and dissolve it. That's it. And of course, in order to know the graphene oxide structure, we also conduct this microscope, okay, to see the morphology, okay, and the size, the shape of this graphene oxide. Well, this will be the preparation method. Okay, basically we prepare not only the nanofluid by varying the concentration of the graphene oxide and putting it into the 5 different fluid that I mentioned just now. Okay, well, this one, the table here is just the calculation only how we prepare the solution. Okay, and of course, come to the most important one, we want to assess whether the nanoparticle is stable or not, whether they are going to agglomerate or not. So what we do is, we're doing the time-lapse spectrophotometry measurement of it. We do the measurement up to 3 hours for a short duration kind of study, and we also continue the study until 2 days to see whether the stability can work for a longer duration or not. Now, let's go to the result discussion. So as I mentioned just now, I'm working on 5 different types of fluid. The first fluid that I'm working on is on the distilled water. I go to the categorization first. So basically, this will be the graphite slag, initially one, and we successfully make it into the graphene oxide. So you can see it's one layer. And this will be the graphene oxide in the solution form and in the dry form. And of course, based on the observation, we found that there is a change in the surface topology upon oxidize the graphite slag into the graphene oxide. And also, but so far it's still good because the dry graphene oxide can be easily dissolved in any kind of solvent, I would say, especially in water. Right, now the first one, my student working on distilled water. Okay, let's have a look onto this graph over here. This graph is for the short duration, working for 3 hours only, while this one is for 48 hours for 2 days, 48 hours over here. Now you can see over here, initially the nanoparticle as location 1 over here, 100% stable. Okay, after 3 hours, portion of the nanoparticle already settled down. Okay, portion of the nanoparticle already agglomerated and settled to the bottom. That's the reason you will see. Okay, that's why you will see actually there is a profile over here. By prolong the duration to 48 hours, you will see some of the nanoparticle further settle down, become unstable. However, still got about 70% of the nanoparticle is stable. About 30% is not stable and start to settle down. We're working on different concentration, and it seems like the concentration doesn't have a very big impact. So it seems like based on the result here, we found that graphene oxide able to sustain more than 70% colloidal stability in distilled water for about 48 hours over here. Now, this could be due to the oxygen-containing group of the graphene oxide. Because the graphene oxide itself already got the oxygen-containing group, so definitely it's able to form the hydrogen bond with the H2O molecule. Okay, that's the reason why it actually has the good colloidal stability inside the distilled water itself. Now, however, we still notice that there is a certain portion of these nanoparticles are going to be not stable and settle down. Now, we believe this mild sedimentation could be due to the existence of mineral or iron. Okay, as the distilled water that we use in the lab is not pure water. Definitely inside got some ion, chlorine, all these kind of ion things. Okay, so this ion can actually suppress the electrical double layer of the graphene oxide, making the graphene oxide not that stable. Okay, so we believe the 30% over here is due to this issue, due to the chlorine or the ion that appear inside the distilled water itself. This will be the first heat transfer fluid that we study. For the next one, we're working on the ethylene glycol. Interestingly, we found that when you're putting in the graphene oxide into the ethylene glycol, there is no sedimentation happen, no matter it's a 3 hour or up to 48 hours. Okay, you can see the nanoparticle remain 100% suspended in the solution. So it's super successful one. We are kind of happy when we see this condition at the time. Now, there was no sedimentation that detected for the graphene oxide when you putting it into the ethylene glycol, okay, even after 3 days. Now, we believe this one could be due to the complete exfoliation of this graphene oxide in this organic fluid. Now, the next one, we try to working on another fluid called the propylene glycol. Now, similarly, for the propylene glycol, up to 3 hours, there is almost no sedimentation occur. How only can be achieved? Okay, even after 48 hours, you can see like only about 10 to 20% is undergo the sedimentation. More than 80% is still very stable. So something good also for our application. It's similar to the ethylene glycol. Propylene glycol is a profit fluid that capable to form the hydrogen bonding. So this could be the reason why the graphene oxide able to stable under this propylene glycol solution. Okay, now let us go into a more fundamental one. We go into the molecular structure again. Looking back into this structure, now do you notice what is the difference between the ethylene glycol and propylene glycol? They actually have 2 OH group over here. They are profit solvent, of course, and they actually have two hydrogen OH group, hydrogen group over here. Now this could be the reason why they actually can enhance the stability of this graphene oxide. They have this similarity in terms of their chemical structure itself. And of course, for distilled water, it is also not bad. Now the next one, we try to working on ethanol. We try to see whether it's effective or not in ethanol. Unfortunately, this photo might be not that clear for you, but we found that after we put the graphene oxide into the ethanol, the graphene oxide straight away go to the bottom already. It might not be clear in this image, but the nanoparticles straight away, they start to settle down already until we not even can conduct the colloidal stability analysis because it's too fast already, okay? The graphene oxide was found to agglomerate almost instantly after being added into the ethanol itself. Now, we go to do some investigation why this happened, and in fact, we noticed that there are two researchers that also found that graphene oxide is insoluble in ethanol. Now, side events could be due to the poor hydrogen bonding between the ethanol and the graphene oxide. In particular, in the more molecular structure level, it could be due to the outer layer of the graphene oxide, which already covered by the hydrophobic alkyl group of the ethanol, making the graphene oxide not able to interact with the ethanol molecule in the bulk medium already. It's mainly due to the alkyl group over here. Okay, due to the alkyl group over here. Okay, making the graphene oxide no longer can interact with more ethanol already. In this case, we notice that ethanol is not a good heat transfer fluid when you mix it with the graphene oxide already. Now, the last one, we try to working on the engine oil. Since engine oil is a very common one that we use in the mobile, anything. Alright, so we try to put it in the graphene oxide into the engine oil. Now, this one, we found that the graphene oxide forming an emulsion or a droplet over here. Okay, a small droplet over here. For the case here, the added GO was found immediately form an emulsion droplet, so also cannot be used. Last it is already forming droplet and settled down already. The engine oil with makeup on the non-polar long hydrogen carbon chain is a poor solvent for graphene oxide. And in fact, we also know just now because the engine oil doesn't have any hydrogen bonding forming ability. So this observation concluded that the incompatibility of the graphene oxide with both ethanol and also engine oil-based heat transfer fluid. So again, this will be a no-no over here. We hope that this outcome will actually give the industry or the future researcher a point of view whereby we know that you can put in graphene oxide nanoparticle into the heat transfer fluid to enhance your coolant, your heat exchanger, but you need to choose the correct fluid. Not all the coolant, not all the heat transfer fluid can be mixed well with the graphene oxide. So something for us to remember as well. In order to further understand the fundamental behind the solubility of this graphene oxide into different solvent, we try to correlate into the Hansen solubility parameter. Now, all the solvent that we are working on, except engine oil, okay, engine oil is not inside this category over here. They actually have their own parameter for solubility, Hansen solubility parameter. Okay. Now, according to literature, by adding in the parameter for the polar bond and the parameter for the hydrogen bond over here, you can know the solubility of your graphene oxide. By adding in the delta P and the delta H over here, you can identify the ranking, how well your graphene oxide can dissolve into it. For example, this one is this one. So it's the highest one. So it's supposed graphene oxide can disperse stable the most in this solution, followed by this one, ethylene glycol. The third one should be this one, propylene glycol, and the last one should be this one, Nano. Okay, this is the ranking based on this Hansen solubility parameter. Again, based on this Hansen parameter, distilled water should be ranking number 1, followed by ethylene glycol, propylene glycol, and ethanol. But if you still remember just now, based on our experimental study over here, based on our result, we found that the best is ethylene glycol, propylene glycol, ethanol is the worst one. So it seems like the ranking here is still the same, but just the distilled water is no longer follow the fundamental here. It's actually dropped into ranking number 3 already. So as I mentioned just now, it could be due to the distilled water itself consists of a lot of iron, chlorine, sodium, all these kind of iron that further disturb the stability of the nanoparticle itself. So with that, we come to the conclusion that the colloidal stability of the graphene oxide in different types of heat transfer fluid has been successfully evaluated. And the most stable one of course is ethylene glycol, followed by this one, and the worst one of course is the engine oil. Of course, we found that it's related to the protic fluid and also the hydrogen group, which enable them to form the hydrogen bonding here. Alright, so engine oil is incompatible. So that's it, the conclusion from this research. So these will be the references that we refer to while conducting this experiment. And of course, the acknowledgement should be given to UCSI University and our research center for providing us the funding to conduct this experiment. Okay, alright, so that's all the sharing from my end. Thank you very much.
Thank you, Dr. Yeap, for your presentation. Okay,
Yeah,
now is Q&A session. Is there any questions that you want to ask Dr. Yeap regarding to his topic? If there's no question, thank you, Dr. Yeap. Okay,
Yeah, sure, thank you.
now we will be moving on to the second presenter. It will be Dr. Lai Li Sze. Dr. Lai, are you here?
Yes, I'm here.
Okay, the topic that she's presenting today will be computational fluid dynamic simulation for carbon dioxide gas transport through polydimethyl siloxane membrane with glycol structure. Dr. Lai, you may actually start your presentation. Thank you.
Okay, thank you for the introduction. So, good afternoon, everyone. I'm Lai from Chemical Engineering Department. So, I will present my project titled Cfd Simulation for CO2 Gas Transport through Pdms Membrane with the Gyro Structure. So, this is a project conducted by my FYP student, Mr. Mahendran, and I would like to thank him for all his effort in conducting the simulation. So first, CO2 is one of the greenhouse gases that have contributed to the global warming, and removal of CO2 is essential because the gas is corrosive and it can damage the pipeline. So this is the global timeline to reach net zero emission for the world, and you can see that if we limit the global warming temperature to 1.5 degrees Celsius, we were able to reach to net zero CO2 emission by 2050. But if we limit the temperature to 2 degrees Celsius, then we're only able to reach to net zero carbon at the end of the century. Malaysia is one of the country commit to reach the net zero emission by 2050. So for your information, net zero carbon emission means that we need to balance the CO2 emission by reducing or eliminating the CO2 emission. So now I would like to explain why we need to conduct the CFD simulation. So CFD is one of the scientific approach that we can use to produce the fluid flow phenomena based on the conservation law governing fluid motion. So we can use CFD to analyze the fluid separation for the membrane technology. So what is gyroid? Gyroid is actually an infinitely connected minimal periodic surface with no straight line and also planar surface. So you can see from the figure here, this is the gyroid structure. And then due to the spatial structure of the gyroid, it has high strength, stiffness, and also low weight and good energy absorption. So for your information, since we are now in the era of Industry 4.0, so it is possible for us to produce this structure by using 3D printing. So that's why it is essential for us to study the potential of the gyroid structure for gas separation. So why do we need to use the membrane technology in this project? Is because membrane is a potential technology for effective CO2 separation with the high surface area and compact design. And also membrane do not involve the phase change, and it is cost effectiveness. So you can see from this figure, the membrane is able to act as the barrier to separate the component, to separate two different components. So one is polymeric membrane. Polymeric membrane is one of the organic membrane that can be easily fabricated, and PDMS is the one of the polymeric material that will be used in this project. And the reason we use PDMS is because it is widely used in the industry due to the properties. So these rheological properties refers to the capacity of the fluid flow And in fact, PDMS is chemically inert, so we will use it for our project. So based on the literature study, we found that there are few problems exist. In order to create a real working model for the membrane, it can be very costly because we need to involve large size of the power plant. And meanwhile, CFD is very useful, and it can reduce the number of the experiments that we need to use to validate our hypothesis. So far, the CfD simulation for the CO2 gas transport across the polymeric membrane with the gyro structure has not been conducted. So in order to close the research gap, these are our objectives. First is to design the 3D model and then to simulate the hydrodynamic profile and to compare the profile with the conventional flat sheet membrane. So these are the methodology that we will use. We have used in the project. First, we will design the model and then simulate the hydrodynamic profile, and finally compare with the flat sheet membrane. The software that we have used is Flux with the student license. Okay, so this software we use it to study the hydrodynamic profile, and these are the stages involved. First, we have the pre-processing, followed by the solver and post-processing. So for pre-processing, we have used the MATLAB SolidWorks and the SpaceClam, and this is the geometry that we have construct. So you can see that this is the gyro structure, and we have the box used to define the boundary, and then this is the flat sheet membrane structure. Okay, so these are the settings that we use in the solver. So you can see that the mole fraction that we use is equimolar of the CO2 and N2. And for the post-processing, after we analyze on the contour, we will do the comparison based on the hydrodynamic profile. The grid-independent analysis was conducted to make sure our solution is independent of the grid size. So after we have conducted the grid-independent analysis, there's insignificant change observed in the velocity magnitude. This has indicated that the machine with our current elemental size might be sufficient to simulate the hydrodynamic profile. The development of the geometry, we use the MATLAB to generate the coding and then use the coding to draw the gyro structure of the membrane. So you can see that when we run the simulation, we only take one unit size of the membrane. And then the material that we use is PDMS. For the development of geometry, we have the inlet and outlet and also the permeate. And then this is the membrane thickness, and the thickness we set it at 1 mm because this is the value of the thickness that we can get from the literature for the CO2 permeability of the PDMS with the structure. And then this is setting for the Flux. So the simulation was conducted until it reached to the conversion. So now I will present the result and discussion. For our hydrodynamic profile, we will evaluate based on two aspects. One is the static pressure and another one is the velocity magnitude. So for the static pressure, you can see from the profile here, when the membrane is at the concave side, it has a lower pressure, and when it reaches to the convex side, it has a higher pressure. And then we can see that the pressure drop is about 10 kPa. So this is mainly because decrease of the wall static pressure coefficient when there is the increase in the degree of the curvatures. So it means that the hydrodynamic profile or the pressure distribution within the membrane can be affected by the curvature of the membrane. Meanwhile, for the flat sheet membrane, the pressure drop is slightly lower compared to the gyro structure membrane. And then the profile is also slightly different, but we can say that the pressure distribution is slightly more uniform as compared to the gyro structure membrane. In comparison, we can observe that there is slight increase in the pressure drop up to 11% by using the gyro structure membrane. So meaning that for the industrial application, usually we will try to optimize the pressure drop across the membrane, because if you have a larger pressure drop, it means that you need to increase the pressure inlet. to compensate the pressure loss during the gas transport across the membrane. So in order to reduce the economical loss, we need to optimize the pressure drop. For another hydrodynamic profile is the velocity magnitude. So you can see here the fluid velocity at the permeate outlet increase when it approaches to the top section. Okay, so this one is because the flow of the gas that will diverge when it moves to the top section for the outlet. Okay, so this can be observed for the flat sheet membrane also. They have the similar velocity profile. We also suspect that when the gas flow from the inlet to the outlet, there is lower time for the permeation here. So as a result, they will have a higher permeation rate to pass through the membrane. And as a result, you will see a higher velocity at the outlet zone. For the CO2 recovery, we calculate based on the molar flow rate at the permeate site over the feed inlet. So based on the calculation, Gyro structure has a slightly higher CO2 recovery, up to 25% as compared to the flat sheet membrane. These values are actually relatively low as compared to the membrane that has been used in the industry. Usually the CO2 recovery should be up to 80% in order to be used in the industry. But we believe that because this simulation was conducted using one unit cell of the gyro structure membrane. So if we run the simulation for larger membrane module, the CO2 recovery might be increased. So the reason here for a higher CO2 recovery for gyro structure may be because it has a larger surface with the curvature structure for the gyro membrane. In conclusion, the gas transport simulation has been successfully conducted and the comparison have been done. And then we have also calculated the CO2 recovery for the gyro membrane and also the flat sheet membrane. And we can decide that gyro membrane is slightly more efficient than the flat sheet membrane in recovering the CO2. So I'd like to thank UCSI University for the internal grant, and thank you for your attention.
Thank you, Dr. Lai. Is there any questions for Dr. Lai's topic? If there's no questions from the floor though, so thank you, Dr. Lai. So we will move on to the next presentation. So Dr. Sum Jing Yao topics will be the removal selectivity of heavy metal cation in micellar enhanced ultrafiltration, a study based on critical micelle concentration. Dr. Sum, you may start your presentation. Thank you.
All right, thank you very much, Poon. So thank you very much for introducing me. Basically, I'm interested to deliver my topics based on the removal selectivity of heavy metal cations in a micellar enhanced ultrafiltrations. So later in my presentations, I would like to introduce a little bit about these micellar enhanced ultrafiltrations as well as conventional removal techniques on heavy metals. The presentations will be followed by objective, methodology, result discussions, and lastly, the conclusions. So basically, for your information, I'm always interested to use a nanofiltrations membrane. So we don't care about which type of membrane first. We care about nanofiltrations. Previously, I spent a little bit time on using these nanofiltrations to treat solutions that contains heavy metals. And actually, I'm always interested is that I want to see if, let's say, in that mixture, in these solutions, in which it contains a mixture of heavy metals, am I able to perform a selective separations among all those heavy metals? And so luckily, based on the ligand formations, so means that actually I tried to design a membrane which can perform the selective separations through ligand formations. And I found that actually this type of membrane can selectively separate the heavy metals into their respective components through ligand formations. So now the project is that I'm trying to think. So now previously I already tried coordinations. Now, what about the electrostatic interactions? So electrostatic interactions is something like a negatively charged will be absorbed, will be interact with a counter ions. Let's say heavy metal actually is a cation, is a positively charged. So why not I try to design a materials which is in the opposite charge, let's say a negatively charged molecule. And then after this, these heavy metals will be absorbed onto the counter ionic complex. So that's why eventually we try to come out with another project in which we try to see whether the selective separations could be occurred by utilizing the electrostatic interactions. So basically, actually, we having a lot of issues when we try to perform the selective separations of heavy metals. For example, for your information, heavy metals, usually they are divalent cationic. What I mean by divalent cationic is that usually they just only contains 2 plus in the heavy metals when it is being ionized. And then they are usually the hydrated radius, they are falls around 0.4 up to 0.5 nanometer, which is extremely small. And previously, we tried to use the nanofiltrations. Yes, it's working fine with these heavy metals. Eventually, all the heavy metals could be rejected more than 99% from the solutions. But on the same time, when we use the nanofiltrations, the pores of the membrane is very small only. So that's why eventually we are using a very high operating pressure. For example, pressure above 7 bars. So in the meantime, it seems like the energy will be consumed a lot in these nanofiltrations. So now we try to think, is it possible if we use a membrane which has a larger pore dimensions? Here we have a candidate over here, which is the ultrafiltrations membrane. So in comparison with the nanofiltrations, actually these ultrafiltrations contains a larger pore. But the problem is that when the pore is larger, what happens is that these heavy metals, they are too small already. So eventually, they are penetrating across our ultrafiltrations. So eventually, we are not able to retain any of the heavy metals if we are using ultrafiltrations. That's why in this project, we are proposing using another surfactant, in which this surfactant is added into the ultrafiltrations process in the solutions over here in order to increase the size of the metal ions by forming the metal micelle complex. So in general, this process is called micellar enhanced ultrafiltrations. So actually this is not a new concept. Previously, a lot of reported works that reporting about the use of MEUF, the micellar enhanced ultrafiltrations, in removal of heavy metals. But what they did is that they tried to put in a lot of SDS into the solutions. They put the SDS in excess. So eventually is that in your solutions, if let's say it contains 2 different types of cations, eventually all those metal cations are electrostatically binded onto the micelles. And these all micelle metal complex are being rejected in the ultrafiltrations process. In other words, it seems like actually we can get a very good rejections, isn't it? For this metal mixture, we get above 90%. But unfortunately is that what we want to achieve is that, is it possible if we try to separate in between the cations A and also cations B? Is it possible if we separate it? So here we read a few articles. They are talking about the influence of the micelle formations together with the presence of metal cations. And based on their reports, actually they found that different types of metal, actually they will have a different impact towards the formations of the micelle. This will be significant, especially when the concentrations of the SDS is very, very low. So, okay, it gives us a very good idea in which we try to see what if we make the amount of the SDS is in limited access. We reduce the concentrations of the SDS so that actually now both of the heavy metal cations, they are fighting to absorb onto this SDS micelle. So this is what we call the competitive adsorptions. We try to utilize these competitive adsorptions to see whether we can achieve a selective separations in this MEUF process. So basically, the work is designed with the purpose to study the presence of the heavy metals in either in the single or binary mixture and the effect of the pH towards the critical micelle concentrations of SDS. So later I will explain to you again what is so-called critical micelle concentrations. After this, I'm also going to examine the removal selectivity of copper chromium binary mixture using a low SDS dosage. So basically, this work can be split into 2 major sections. The first major section is that I'm going to measure the CMC of the SDS. So CMC means the concentrations of the surfactant at which the micelle is started to form. So for your information, the micelle could be something like this. It could be a globular structure, which is in a very small radius only. Initially, the SDS molecule is just only a straight chain, something like this, and then together with the hydrophilic head. Original is like this, but whenever the concentrations of the SDS is high enough, usually all those hydrophobic tail, they will be connected to each other, and eventually they are forming a micelle. So the concentrations of the SDS at which this micelle is started to form is called CMC. So the first sections, I'm determining the CMC, and then actually I prepared a few different systems, which the first system is just only a pure water without anything, without any heavy metals. And the second system, actually it contains 100 ppm of copper or chromium, means that actually this is just only a single heavy metals. The last one actually is a binary mixture of copper and chromium. Total concentrations is 100, means that actually 50 ppm of copper and also 50 ppm of chromium. Not forget to mention, actually the pH of all three systems are adjusted to pH 3, pH 10, and also without any pH adjustment. So after we determine this CMC, eventually we will carry a filtration process, which we are using a polyether sulfone ultrafiltration membrane, which the molecular weight cutoff is around 10k Daltons. And then in the feed, actually we try to dose in an 100 ppm equivalent binary mixture of copper and chromium. The pH were adjusted to pH 3, pH 10, and without pH adjustment. After this, we also dose in these 7 millimolar SDS concentrations. So from where we obtain this value, basically is obtained through our first sections over here. Alright, so now this is the results that we obtain based on the first sections to determine the CMC. I would like to draw your attention onto the first graph. This is the system in which this is a conductivity versus the SDS concentrations free of any metal ions. So means that actually this is just only the CMC that we measured in the water only. You may realize that when we try to increase the SDS concentrations, conductivity is increased. This is because we are adding more SDS molecules, which is ions. So that's why these all ions, they are free moving. They will contribute to the increment of the conductivity. But until a certain point, now, at this point, the micelle is already started to form. So that's why eventually the free moving SDS will be reduced. So that's why you may realize that at first, before this, the slope is increased. The slope at the first sections is more greater than the second sections. So this is the turning point at which we call it as CMC. This is the point at which we determine as CMC, critical micelle concentrations. You may realize that lower the pH, for example, pH 3, the CMC could be lower, which is at around 6 millimolar. Without pH adjustment, which is around pH 5 to 6, the CMC will be around 7 millimolar. This is the case for the water, blank water only. But if we try to put in 100 ppm of copper cations, what will happen? We observe that the CMC value is further reduced. For example, for this pH 3, the CMC is around 4 millimolar. Compare it to the 6 millimolar over here. On the other hand, without any pH adjustment and pH 10, 6 millimolar compared to the 7 millimolar. So this is the case for the Cu. It seems like the presence of the Cu, if actually it can be served as the bridge to link all the SDS molecule together. In other words, the presence of Cu enables the SDS micelles to be formed at even lower concentrations. But on the other hand, if we try to put in 100 ppm of chromium, so disappointed that eventually all those CMC, actually they are still remain almost the same if compared to the first system, 6 millimolar compared to the 7 and also the 8. So it seems like actually the presence of chromium, actually it does not contribute to the CMC formations. And lastly, it's quite interesting to us that we try to put into a mixture 50 ppm of copper and also 50 ppm of chromium. And then we realize that now at pH 3, the CMC is around 4 millimolar. It is quite comparable to our second system, which just only copper. And then after this, we try to, without any pH adjustment and also pH 10, we realize that actually the CMC is not far away, it's not deviate that much if compared to the system that contains only copper. Actually, it gives us a little bit hints that in a binary mixture that contains copper and chromium, actually the copper is the one taking initiative, is the one which has a preferential absorption towards the SDS micelle. So actually it gives us a clue that in this system, actually we probably can perform a selective separations in which we expect that the Cu eventually will be easily absorbed onto the SDS micelle, but the chromium is not interested to be bound onto this SDS micelle. So by getting this result, we further proceed to the filtrations. As expected, if we do not put in any SDS, it's very obvious that the rejections for both metals could be very low, 27 and also 4% only. But with the presence of SDS, the rejections for both metals are greatly increased. For example, at pH 3, we observe that the rejections could be somewhere around 45 and also 17 for copper and chromium respectively. The rejections actually is the lowest among all another 3 different pH. This is because at pH 3, usually there will be a presence of H+. So H+ actually is a proton, and for your information, the proton itself is very highly diffusive and hence actually is another competitor to these adsorptions. Eventually, because of the size and the diffusivity of this proton, all those SDS micelles actually are just only bound to this H+, and hence the rejections onto this copper and also chromium will be reduced. But we also observe that without any pH adjustment, the selectivity removal of the copper will be much more higher if compared to the chromium. The highest selectivity is obtained at this no pH adjustment system. So actually these results could be explained based on 2 different explanations. The first explanation, actually I can explain it based on the conductivity over here, based on the CMC over here. We observe that in the binary mixture, it seems like the copper actually is taking the initiative to bound with the SDS micelle. On the other hand, I also can explain it based on the ionic speciations of both copper and also chromium. You may realize that within the range of the pH from pH 3 until pH 8, the copper actually is quite consistent, actually is steadily presented as Cu2+ from pH 3 up to pH 5. However, beyond pH 5, the copper hydroxide complexes will be formed. On the other hand, if we look onto this chromium, the graph is extremely messy. From pH 3 until pH 5, you may realize that at this pH 5, most of the Cl3+ is already converted into the chromium hydroxide complexes. Bear in mind that these all hydroxide complexes, they has reduced in the valence charge, and also the hydrated radius could be larger. So when we thought that larger hydrated radius and also lesser valence charge means that the diffusivity of this chromium is reduced already. Eventually, the copper 2+ will gain advantages over this Cl3+ because of Cu2+ is still remain as Cu2+, and hence the diffusivity will be much more higher if compared to the chromium hydroxide complex. So lastly, this is my conclusions. We do found that the lower CMC obtained in these acidic conditions, which is at pH 3, than in the neutral state and in the alkaline conditions. The lowest value of this CMC could be obtained in the presence of 100 ppm of copper at pH 4. Highest removal selectivity was obtained with the dosage of 7 millimolar of SDS and without any pH adjustment, which the rejections could be obtained with is around 66 of copper and also about 20% of chromium. So this is all the references that we referred to when we try to conduct our research. Last but not least, allow me to acknowledge Swee and also our internal grant, REIG, for sponsoring this project. And I would also like to thank my FYP student, Kok Wen Sin. Actually, she did really well in the completions of this project. All right, I think that's all for my presentations today. Thank you very much.
Thank you, Dr. Sum. Is there any questions regarding on Dr. Sum's topic? Okay, if there's no question, then we will move on to the next section. Thank you, Dr. Sum.
You're welcome.
The next presenter will be Dr. Chai Pui Vun. His topic will be green approaches to polysulfone based on membrane preparation, while dimethyl sulfoxide and eco-friendly natural additive Arabic gum.
Okay, very good afternoon to everyone and those to all the presenter, to all who in the room right now. Okay, I wish everyone is safe. Okay, let me just start my presentation here. My presentation title today would be looking to the green approaches on fabricating the polysulfone-based membrane by using green solvent, which is dimethyl sulfoxide, as well as the natural additives such as Arabic gum. Now, in the pursuit of this global environment sustainability, researchers, experts, scientists, and engineers from various sectors and backgrounds, they are inclined to develop or improvise product based on its sustainability. The demand for the sustainability development in the current society is extremely high, owing to the depletion of the various resources that is alarming to the future generation. In the current industrial needs, it requires experts and engineers to brainstorm innovative solutions to redesign, optimize, and reduce the energy consumption of the process. On the other hand, in the present research and development practices, it requires researchers and scientists to adhere to the design of chemical process and product that could minimize or even to the extent of eliminate the generation of hazardous substance that is deemed harmful to the environment. So, therefore, in line with this 12 pillar of green chemistry, green approaches should be adopted in the current advanced technology practices such as membrane technology to promote sustainability in the product. Okay, membrane technology is one of the established advanced technology that had proven its effectiveness in tackling the global water security challenge in various sectors. It is recognized as a sustainable and green technology that often being practiced in the municipal as well as in industrial wastewater treatment globally. However, despite their undisputed application and advantages, membrane technology itself still yet to be claimed as a fully sustainable technology owing to the usage of this conventional solvent itself. So therefore, in this study itself, we would like to see what is the problem statement here. Can the green solvent itself replace the conventional solvent, or will the good performance of the membrane remain the same after we use the green solvent, or do we have the comparable performance, or we have the same performance, or we have a better performance? Now, to solve this problem itself, we look at the approaches here. As I mentioned in just now, we use DMSO as a green solvent. Now, second, we use the Arabic gum as a performance enhancer. Now, just to touch a little bit on this, green solvent is something that is sustainable. It's a green approaches that can minimize the harm to the environment, while the natural additive is that I use, which is Arabic gum, is amphiphilic, water soluble, that can help to enhance membrane performance. Now, at the same time, it is eco-friendly to the nature as well. Now, this is some of the past study has been presented by other researchers from the time 2015 until 2020. So if you can see from here, a lot of green solvent have been used here. So the significance of my study here would be, first, I use the MSO, though that it is already studied last by other researchers, but this time I added Arabic gum. It's a green additive to this study. So this would be the significance of my study. Now next, the objective here, with that being said, my objective that I derived from this literature study itself, of course, I would like to evaluate the green approaches in membrane fabrication, namely to explore few solvent. Of course, first, DMSO is the main one because we figure out DMSO is the best among the styrene, TEP in our approach. And after that, we come to enhance the performance in the presence of aerobic gum. And after that, we evaluate the membrane performance and anti-fouling behavior. So let me continue. So the methodology for my experiment would be, I started it with the fabrication of the membrane. First, I collect the item, purchase it, and I fabricated the membrane using the phase inversion method. Then I evaluate the performance via these 6 characterization methods. So this would be the formulation that I use, namely N1, N stands for NMP, D1, D stands for DMSO, C1, C stands for styrene, and T stands for TEP. With the percentage of polymer, I remain it as the same. Now, let's look at this result. I'm quickly moving to the result part of this. As I mentioned, first I need to screen the green solvent selection. First, I need to know what is the solvent that I'm going to select for my whole study, for this study itself. First, if you can see from the DMSO, the appearance for the DMSO and TEP is acceptable, while for the styrene is most likely is not acceptable as compared to TEP and DMSO. Hence, we opt for, I'm not sure what happened to the presenter. Okay, so I'm not sure. Okay, so here we will select DMSO and TEP. Now from this study itself, the next we want to screen the green solvent based on the energy use and homogeneity of the solution. First, we would like to see what happened to the homogeneity of the solution. We can see that all homogeneity of the solution, it performed better. So I would say all of it, N1, D1, T1, and C1 is acceptable. But by looking what we have done, we have did previous slide just now, styrene is not acceptable because it has the least favorable appearance, while for the N1, D1, and T1 itself, we can look from here. The energy consumption for the TEP, the T1, is slightly higher as compared to D1 and N1. And hence, from all this screening, we have concluded that we selected N1, which is our control system, while the D1 would be something that we want to study. Now, let's look at the characterization from here. So we are going to focus on N1, N2, D1, and D2. So contact angle, what is contact angle? Contact angle is the measure of whether the membrane like the water or not. The lower the value, the better the hydrophilic. It becomes more hydrophilic for the membrane itself. So if you can see from the D, we only can compare N1 to D1, N2 to D2. So let's look at N1 and D1. So you can see from N1 and D1, for D1, you will have slightly lower value as compared to the N1 value. Hence, N1 values does show a comparable result. As for the D2 and N2 result, as for the N2 and D2 result here, we can see that D2 is lower than N2. So it is shown that this D2, the membrane that fabricated using the DMSO, also show a better hydrophilicity. And owing to this improved hydrophilicity, the porosity and the pore size increase accordingly. So as you can see from the curve itself. Next, we are going to look at the membrane performance for the water flux, rejection, flux recovery ratio as well. This is the 3 main things that actually we will study based on the result. The first thing that I would like to touch is about this water flux. If you can see, what we really observe is the N2 and D2 itself. D2 do produce a comparable result as compared to N2 result. which means that even though I change it to green solvent, I also can have a higher water flux that is comparable by using the control system. Next, we want to compare with this rejection. The rejection also show a higher result. This could be due to the presence of the Arabic gum, which is negatively charged in the nature. For example, my membrane is negatively charged. Then my particulate, which is congruent, is also negatively charged. So normally when you have a negative and negative charge, it will reject one another. Now lastly, I perform one characterization performance that is named as a flux recovery ratio. This flux recovery ratio also show a good result as according a comparable, which is 93.29 and also 94.48. So it's comparable with the N2 membrane itself. Now with all this result itself, I have come to the final conclusion for this. That is, first, the membrane was successfully fabricated, and the comparison will make among different solvents, and based on the energy, the appearance, also as the homogeneity, DMSO was selected as a green solvent in this study. Now the membrane performance also proved that membrane prepared with DMSO as green solvent and also eco-friendly natural additive Arabic gum also show comparable membrane performance. And overall, D2 membrane show a better result as compared to other membrane result with this characteristic. This one shows that DMSO is a good green solvent to be adopted to produce a comparable membrane performance with the conventional solvent. Now the recommendation for my study is that I would like to continue to develop more DMSO related membrane and also explain more combination and also include more characterization and explore this in terms of wastewater treatment. So with that, I would like to thank UCSI, also UCSI Research Grant Innovation, RAIG FP, for sponsoring my study. Thank you so much.
Thank you, Dr. Chai. Is there any questions that participant would like to ask Dr. Chai on his topic? If there's no questions, today research curriculum has came to an end because all four presenters already presented their presentation, their research and finding. So I would like to give all participants a gentle reminder again that if you haven't filled up the attendance form, you may go to the chat session there. There will be a link and you just click on it to fill out the Google form to take attendance. And if there's nothing questions about any of the research topic, the research curriculum will be for this session will be end for now. And also the research curriculum will be actually held for every month. So the next one will be on March, and the dates and also the details will be announced later. And if any lecturers or maybe students that are interested in sharing their research and studies through this research curriculum, you can actually register your participant to Dr. Tong. If there's nothing else, thank you everyone for participating in the research curriculum. Thank you.